Welcome to this explainer. Today, we are embarking on a seriously epic spatial journey. We're going to start way up high in the atmosphere, drop down onto the continents, plunge right through the ocean's wildly dynamic surface, and then sink all the way down into the absolute darkest, most pressurized trenches on planet Earth. We're going to decode the hidden mechanics of our oceans. It's this incredible, interconnected system of heat, salt, and staggering topography that quite literally makes life on this rock possible.
Okay, let's dive right into this. Here is our map for today's descent. First, we'll look at the hydrological cycle, then uncovering the ocean floor, ocean surface temperatures, the secrets of salinity, and finally, deep water stratification.
All right, starting at the very top, Section 1, the Earth's hydrological cycle. Let's look at how water circulates.
Now, before we really try to understand the deep, we have to pull back and look at the macro view. The sheer dominance of the oceans is immediately obvious, right? 71% of all planetary water is locked right there. But what's really fascinating is the constant exchange happening just above it. Get this. Of all the water that falls onto land as precipitation, nearly 59% of it returns straight back up to the atmosphere through evaporation. And that's from both over the oceans and terrestrial environments. So the hydrosphere is essentially this massive non-stop recycling engine.
So what actually happens to that remaining water, the stuff that doesn't immediately evaporate back up? Well, it becomes our freshwater reserves. It runs off the surface into lakes and streams, it seeps deep into groundwater sources, becomes soil moisture, or it just gets locked away in these massive glaciers and ice caps. A tiny fraction is even held within the atmosphere and within living organisms, including us. But ultimately, gravity insists that water seeks its lowest point, and that brings us right back to the Great Basins holding that 71%.
Which brings us to Section 2, uncovering the ocean floor. Let's head beneath the surface.
If you were to somehow pull the plug and completely drain the oceans, you wouldn't just find a flat, featureless bathtub down there. No way. You would find a landscape far more dramatic than anything we have up here on land. As we step off the beach, we first walk onto the continental shelf. Think of this as the shallow, flooded edge of the continent. On average, this shelf is about 80 kilometers wide, but the variation is just staggering. Take the Siberian shelf in the Arctic Ocean. That thing stretches an astounding 1,500 kilometers in width. It's a vast underwater plain, and it varies in depth from a mere 30 meters down to about 600 meters. But eventually that shelf runs out, and when it does, we hit the continental slope. Now this is where things get really serious. The gradient steepens significantly, dropping at an angle of roughly 2 to 5 degrees. As you slide down this slope, you leave those sunlit margins completely behind, and you rapidly plunge to depths anywhere between 200 meters and 3,000 meters. At this point, we are officially leaving the continents and entering the true oceanic abyss.
Down at the very bottom of these basins, we find the absolute extremes of our planet, the ocean deeps, or trenches. As many as 57 deeps have actually been explored so far, and as you can see, the Pacific Ocean heavily dominates here. It holds 32 of these massive subduction zones, compared to just 19 in the Atlantic and a mere 6 in the Indian Ocean. These are literally the darkest, most pressurized environments on Earth, and sprinkled all across this vast, deep canvas are a whole host of minor relief features. We're talking about massive volcanic mountain chains called Mid-Oceanic ridges, towering solitary seamounts, deep submarine canyons carved right into the slopes, flat-topped guyats, and coral atolls. The ocean floor is a rugged, violent, and highly dynamic landscape. But, okay, now that we know what the container looks like, let's travel back up to the surface to actually examine the water itself.
Moving on to Section 3, ocean surface temperatures. Let's talk about heat from the sun. Arriving back up in the sunlight, we find that the sun's heat doesn't hit the Earth evenly. There is a very clear mathematical relationship at play here. Ocean water temperature generally decreases by roughly 0.5 degrees Celsius for every single degree of latitude you move away from the equator. So around the 20-degree latitudes, we see warm averages of about 22 degrees Celsius. Move up to 40 degrees, and it drops to 14. By the time you finally reach the poles, the water is sitting right at a freezing 0 degrees Celsius. Furthermore, if you take a temperature depth profile anywhere, you'll see a sharp drop. Temperature heavily decreases with increasing depth simply because we lose the sun's reach.
Now, what's really interesting about this is a geographical quirk you might not expect. You would naturally think the absolute hottest water is sitting exactly on the equator, right? Actually, scratch that. It isn't. The The highest temperatures are recorded slightly towards the north of the equator. Because of the specific way land and water are distributed around the Earth, the oceans in the northern hemisphere actually record relatively higher average temperatures than those in the southern hemisphere.
Section 4. The secrets of salinity. The invisible force.
So, temperature is really only half the story. To truly understand how the ocean moves, we have to look at the invisible force that controls water density, salinity. Let's quickly define our terms so we're all on the same page. Salinity is calculated as the amount of salt, measured in grams, dissolved in exactly 1,000 grams, so 1 kilogram, of seawater. We express this crucial metric as parts per thousand, or PPT. It is absolutely one of the most fundamental properties of seawater.
And when it comes to salinity, this specific number is a vital benchmark, 24.7 parts per thousand. Oceanographers consider this exact concentration to be the strict upper limit used to demarcate brackish water. So, anything saltier than this crosses the threshold out of brackish territory and into the realm of true marine seawater.
Now remember how we talked about the surface layer? It's basically a highly dynamic mixing bowl. The salinity up here fluctuates constantly based on several massive natural processes. Evaporation pulls fresh water out, leaving salt behind, while precipitation just dumps fresh water back in. Along the coasts, heavy freshwater flow from rivers dilutes the sea. At the poles, freezing ice rejects salt into the water, while thawing ice melts fresh water back into it. Even the wind plays a role by physically pushing and transferring water to different areas, and massive ocean currents constantly stir and redistribute these varying salt concentrations.
To really put standard ocean salinity into perspective, look at the extremes found in landlocked bodies of water. The ocean is salty, sure, but Lake Van in Turkey sits at an astonishing 330 parts per thousand. The Dead Sea follows closely behind at 238 parts per thousand, and the Great Salt Lake at 220. These hypersaline environments are dense, thick, and radically different from the standard open ocean. But here's the thing, even out in the open ocean, much smaller differences in salt content have massive consequences.
Let's move to and see how this all builds into our final section. Section 5. Deep water stratification. Let's take one final plunge into the abyss. Let's leave that chaotic, sunlit surface behind and plunge back down into the dark. There's a very stark contrast between the top of the ocean and the bottom. As we just discussed, the surface zone is highly active. Water is lost to ice and evaporation, and fresh water is constantly added by rain and rivers. But at depth, salinity is remarkably fixed. Down in the darkness, there's no mechanism for water to be lost, and there's absolutely no way for new salt to be added. The deep zone is basically frozen in time, maintaining a highly stable, very different profile from that turbulent surface resting high above it. And as we descend from those lower salinity surface waters to the higher salinity deep waters, the transition isn't always some gradual fade. We actually hit a distinct, sharp vertical zone known as the halocline. Here, the salinity increases sharply, creating an invisible physical barrier right in the water column. It's kind of like oil sitting on top of water. The lower salinity water naturally rests above the denser, higher salinity water.
So, the absolutely crucial point here is this. Salinity, temperature, and density are entirely interrelated. Increasing the salinity of seawater naturally causes its density to increase. As a result, high salinity seawater becomes really heavy, and it physically sinks below the lower salinity water. Combined with the freezing cold temperatures of the deep, this leads to intense stratification. The ocean isn't just a stirred-up uniform pool. It is a sharply layered, three-dimensional cake driven by the endless push and pull of sinking salt and frigid temperatures.
Which brings us to the ultimate question. The hidden mechanics we've uncovered today rely on a very delicate balance. If ocean stratification permanently traps this dense, highly saline water in the deep, acting as a massive global stabilizer, what actually happens if changing climates fundamentally alter the evaporation, the ice melt, and the temperature, and therefore the overall density of the waters resting above? If the surface fundamentally changes, does the mighty, layered foundation of our deep oceans eventually collapse? I'll leave you to ponder that one. Thanks for joining me on this explainer, and keep questioning the mechanics of our world.